Good day, dear participants. With your permission, I present a work, Training Neural Network Method Modification for Forward Error Propagation based on Adaptive Components. Feed-forward neural networks are widely used in artificial intelligence, compressing layers of neurons with direct signal propagation from input to output. They rely on adaptive elements that enable training and adjustment of weight through methods like the backpropagation algorithm, which uses gradient descent. The development of this network involves defining the architecture, initialization weight, and iteratively training and testing the model until satisfactory performance is achieved. However, backpropagation can get stuck in local minima and saddle point, necessitating careful hyperparameter selection and optimization techniques. This research aims to develop new optimization methods for backpropagation to enhance training speed and accuracy, ensuring stable convergence and reducing the likelihood of local minima entrapment. The known research emphasizes the need to address the complexities in managing and tuning feed-forward neural network due to individual adjustment of training rate coefficients for adaptive parameters, which increases computational resource, training time, and the risk of instability. The REBI underscoring the importance of developing new optimization methods to enhance training efficiency and model stability. One possible optimal adaptive element to improve the backpropagation algorithm could be the adaptive training rate, ATR. This element will dynamically change the training rate depending on the gradient obtained at each training step. In this work, a training algorithm for forward propagation neural network has been developed based on the backpropagation algorithm, which through the use of adaptive elements such as adaptive training rate, adaptive initialization of neural network weights, adaptive regularization, adaptive neuron activation function, adaptive change in neural network architecture, adaptive change in the size of the mini-batch made it possible to achieve almost high accuracy of their training on both the training and validation data sets with a minimum number of iterations. A complete mathematical description of the developed algorithm is given in this work. The proposed algorithm for training feed-forward neural network allows to formulate the following theorem. Training algorithm for a feed-forward neural network with adaptive initialization of weight, adaptive training rate, adaptive regularization, smooth loss function, adaptive activation function, adaptive change in training rate over time, adaptive change in neural network architecture, and adaptively changing in mini-batch size coverage to an optimal solution to the training task with probability 1 if the following conditions are thus met. Proof of theorem is given in this work. The proposed algorithm for training a feed-forward neural network with many adaptive components has wide practical application in machine learning and artificial intelligence, such as image processing, where it enable high accuracy object recognition through adaptive techniques and efficient data processing. This approach, which includes adaptive weight initialization, training rates, regularization, and mini-batch size adjustments, can be applied to fields like computer vision, natural language processing, and medical data analysis, as well as in debugging helicopter turboshaft engine parameters to ensure consistency across control elements. In the input signal approximation task, the dependence on the specific fuel consumption of the gas generator rotor RPM for the TB3117 turboshaft engine, which represents an element of the engine throttle characteristic, is presented. This figure shows the input data indicated by points which are approximated by broken lines for clarity. As a part of the computational experiment, a forward propagation neural network was used, the input of which are the parameters of the gas generator rotor RPM and specific fuel consumption, and the output are their optimal values. During its training with the both proposed algorithm, the dependence of the accuracy, top figure, and losses, bottom figure, of the neural network were obtained, in which the blue curve means training on the training sample, the orange curve means validation on a control sample. From top figure it can be seen the limiting values of the accuracy reaches 1, and from bottom figure show that the maximum loss values do not exceed 0.025. This indicated a high degree of efficiency in training the model of the provided data and the ability of the model to generalize to new data with a high accuracy, which makes it potentially suitable for solving the task of helicopter turboshaft engine parameter debugging. The results of the research are presented in this slide. There are diagrams determining the influence of the training rate on the final standard deviation, diagram determining the influence of the number of hidden neurons on the final standard deviation, diagram determining the influence of the number of epoch passed of the final standard deviation. The resulted figure helps identify areas where each class 2 likely to be found and defines refined limit values of gas generator rotor RPM at levels 0.1, 0.5 and 0.9, allowing for accurate determination of the optimal gas generator rotor RPM to achieve specific fuel consumption targets. The admissibility of adjustment gas generator rotor RPM to achieve maximum permissible specific fuel consumption values is highlighted, as doing so may exceed safe engine operation parameters, leading to issues like engine overheating or flight instability, emphasizing the importance of maintaining optimal engine conditions. The work carried out a comparative analysis of the solution to the task of helicopter turboshaft engine parameters debugging based on a feed-forward neural network with adaptive elements using both the training algorithm proposed in the work and the delta-bar-delta algorithm. The first and second type errors were calculated in obtaining the gas generator rotor RPM boundary values to achieve the required levels of specific fuel consumption. The obtained results show that the use of the feed-forward neural network with adaptive elements trained on the basis of the algorithm proposed in the work made it possible to reduce the type first and second errors by 1.65 to 1.71 times compared with the use of the delta-bar-delta algorithm for its training, and the significance level is 0.01. The conclusions are presented in this slide. Thanks for attention.